This week we will talk about atoms, and this is a continuation of the previous session when we finished with Lavoisier. Lavoisier being one of the most important chemists in modern history, and even more, he is called like the father of modern chemistry himself. And he got this recognition mainly because of his contribution to the quantitative measurement applied to chemical problems and his law of conservation of mass. About the society and the history of society in those times, we must know that in Europe, but also in other parts of the world, was starting what is called the Age of Revolutions. So in France, started the so-called French Revolution, on which Lavoisier lost his life. He was decapitated at a young age, which is a pity because he was such a great scientist himself. But also in other parts of the world, there was like independence wars and revolutions, like in America, in the United States, and different parts of the world. We are also in a point where is the end, or we are in the period of so-called the Age of Enlightenment, when there is all this group of mm, scientists and natural philosophers that were defying the ancient knowledge of the Greeks and bringing new tools and development of new theories for the nature of matter. Remember also that we had a period of the so-called scientific revolution, which is also, we can say, a part of, or at the beginning, a little before than the age of revolution, but it's a revolution in itself that we call names like Isaac Newton and his publications Principia Mathematica, which is one of the most influential books that sometimes is marked like the beginning of the age of revolutions himself. So in this context, chemistry and physics, they take the modern notions that we still study today. And in that sense, we will start to recognize several names that we use today for process like pressure and uh, calculations in stoichiometry, and all these things started to be developed at this period of time. So let's start. So it's in this period of revolutions, in the age of revolution and the age of enlightenment at the end of the 18th century, that Antoine Lavoisier and Joseph Black clearly show the relevance of the quantitative measurements for the development of chemistry. Mainly Lavoisier, who is attributed to be the father of modern chemistry, developed these methods further. And as we saw in previous session, his contributions proved to be useful to really understand the nature of matter and to replace old and wrong theories, like, for example, the phlogiston theory. Another example then is Joseph Black, who also took this approach, probably or mostly influenced by this age of enlightenment and the philosophical works of René Descartes, for example, or the development of the scientific method, that Joseph Black used this approach for understanding the neutralization of acids with calcium carbonate. So we know that he was working with calcium carbonate, and it's with this compound that they have found that, for example, air, it was not just a simple gas, but it's a mixture of different gases. About the neutralization reactions, we know that in the 18th century, chemists already had experience for a long time. So much before than the 18th century, chemists had experience with neutralization and salt formation reactions. If you remember, even during the alchemy period, salt was proposed like one of the fundamental materials for solids. Mm, so in the relevance here now is that during this 18th century, chemists were trying to understand how is the neutralization process and the salt formation process. They also knew that acids may produce hydrogen from the reaction with some metals, like for example zinc, tin, or iron. And they knew that acids and bases they can produce different changes in dyes, different colors, and they differentiated also acids and bases based on their taste. So they diluted the basic material and they could even identify an acid or a base based on their taste, which is dangerous and we don't do today. But as I just said, neutralization and salt formation reactions are not new at the time, and we have example or a good example with Johann Glauber, who at the beginning of the 17th century he already had a prosperous business selling what he called like Glauber salt, which is basically sodium sulfate. And he produced this material like an elixir or like a medicine for different types of disease at the time. And even before that, you can remember the case of Arabic alchemists who were also producing different salts for the same purpose. What makes everything different is precisely the use of quantitative measurement. So even these reactions were known before. Now, during this period of history, is when chemists start to realize and quantify precisely the amounts of material that react to each other. And for this purpose, it was Jeremias Benjamin Richter, a German chemist, who who did the quantitative measurements of neutralization reactions. He is attributed to be the person who introduced the concept of stoichiometry and equivalent weight. So he published this concept of equivalent weight in 1792, and with his measurements he concluded that fixed and definite amounts are required for the neutralization reaction. So this was quite revolutionary because it was not too much time after that that other scientists or chemists they started to ask if this proportion or these definite amounts they were only characteristic for neutralization or for chemical reactions in the liquid phase or if these different definite amounts they are also a property of matter itself. And in this case, or in this debate, in this question, there were two different trends. One, which was more supported by a chemist called Claude Louis Berthollet, and the other by Proust, that we will show later. According to Berthollet, he believed that the composition of a substance depends on the method how it was produced. So if you were producing a material and during the synthesis process you added more of one of the constituents, then you will end up with a product substance which contains more of that original material in excess. However, Proust argued differently and the opposite, and he believed that there was a definite proportion of of the material in a given substance. About Berthollet, we can say that he was working directly with Lavoisier, and he made important contributions to chemistry in the fields of nomenclature, again like Lavoisier, and he was the first to produce sodium hypochlorite, which is a bleaching agent that we still use today. In clear opposition to Berthollet's view on the definite composition of materials, we find another French chemist. His name was Joseph Louis Proust, who made his work mainly in Spain because he didn't want to have the same fate like Lavoisier, who was executed during the French Revolution. And with his work, he could clearly demonstrate that there was definite proportions in substances independently from the method how they were prepared. First, he tried with copper carbonate, and he demonstrated that independently of the synthesis method, or even if the material was found in nature, so independent of the method, this compound always contained the same amount of copper, oxygen, and carbon ratios. So the proportions were constant for these materials. So he, from his measurements, he could conclude that copper carbonate was always 5.3 parts of copper, 4 of oxygen, and 1 of carbon. This is what we know today like the law of definite proportions or Proust's law. And even more, he could demonstrate that Berthollet's conclusions were based or biased by inaccurate analysis or insufficiently purified starting materials. About his life, we know that he started to study chemistry directly from his father, who was an apothecary in Angers in France, and later on he moved to Paris, where he was also an apothecary. But later, during the French Revolution, he moved to Spain, and there he was teaching at a university in Salamanca and Segovia. But later, when Napoleon invaded France, then he was pushed to go back to France, where he died. Finally, this contribution of Proust, the law of definite proportions, we can analyze like an evidence for the atomistic view. And this is something interesting to analyze how we are talking about scientific development which was done only 300 years ago. So it's quite a short time. And still at that time, it was not completely clear or not completely sure or, or it was not proof enough that there is an atomistic reality, so that the matter was really built from atoms as it was proposed by Democritus in the ancient Greeks time. So if you remember Democritus and Leucippus, they were the first to propose that matter was built from indivisible atoms. But you should remember also that this theory or this concept was mm, neglected by Aristotle. And then, since Aristotle, let's say that the favorite or the most common trend was to believe that matter was built from a continuous matter. However, it was Boyle who, while experimenting with gases, demonstrated that this couldn't be the case because if you have the possibility to compress a gas, it means necessarily that there is some empty space between the atoms so they can be pushed together. If the matter was in reality like continuous, then it shouldn't be the case because you couldn't push the atoms closer. Uh, Now, with the definition or with the contribution of the law of definite proportions, it also clearly shows that matter seems to be composed of bits of elements or of matter that they combine in definite proportions. And this is more easy to understand if you consider the atomistic theory. After Proust, there was another very important contribution from an English uh, chemist called John Dalton. In this slide, I highlight two of his major contributions. The first, then, is the law of multiple proportions, when he states that two elements can be mixed in different amounts but fixed proportions. So it is one step further than the Proust law, in the sense that he says, like, he takes an example like carbon monoxide and carbon dioxide. So he says that carbon and oxygen will always react in a multiple amount. Like, for example, we know from Proust law that 3 parts of carbon will react with 8 parts of oxygen to produce carbon dioxide. And this is independent of the method how the carbon dioxide is produced. But what is shown by John Dalton is that this same carbon and oxygen, they can react also to produce carbon monoxide, which is made of 3 parts of carbon and 4 parts of oxygen. And that's why the name of the law, the multiple proportion, because this ratio between carbon and oxygen, they follow a multiple proportion trend, let's say. Besides this law of multiple proportions, based on that results, he proposed the first table of atomic weights. So from long time ago, it was known that hydrogen was the lightest element or gas, and arbitrarily it was given the weight of 1, and everything else was compared to hydrogen. And based on this assumption and the results of experimentation, he gives the atomic weight, or the first table of atomic weights for the elements known. However, he makes a mistake because he assumed that molecules were built pairing single atoms, just with some exceptions that were clear to him, like the case I just mentioned about carbon monoxide and carbon dioxide. So, for example, one of the mistakes when he built this table is in the case of water. So he assumed that molecules were most of the cases formed by the reaction of one atom of one element with one atom of the other element. But it's clearly not the case because, for example, he represents water like one atom of hydrogen plus one atom of oxygen, and because of this, he gets wrong the mass or the weight of oxygen by a factor of 2. This problem was solved later with development of electrochemistry. Despite the mistakes he had on the table of atomic weights, his work on the law of multiple proportions was highly influential, and in 1808 he publishes a new system of chemical philosophy, which we can consider like the end of the alchemy goal of metal transmutation, because from this point on it was clearly distinguishable that each metal is built by different types of atoms, and therefore the transmutation or the modification of these atoms, it was not possible, at least not with the energy levels which are commonly used in chemistry. The solution for the problems in the table of atomic weights proposed by Dalton, it came from the experiments of William Nicholson and Anthony Carlisle, and they proved that the volume of hydrogen was double than oxygen, and therefore if you use the hypothesis of Avogadro, then you can be sure that the Dalton's formula for water is wrong. So it was not only one atom of uh, hydrogen plus one atom of oxygen, but the correct, which contains 2 atoms of hydrogen and one of oxygen. However, the proportion which is the basic principle of the formula or the law still holds. So the proportion of 1 to 8 by weight between hydrogen and oxygen is still valid, even though he made the problem with the calculation for the atomic weight of oxygen. Mm, However, now I would like to talk a little bit about the history of electricity, and we know that since ancient Greek times, uh, for them it was known that amber, when rubbed, it can attract some light objects. This is something that we experience when we were children, that after you comb your hair, you can attract small pieces of paper and things like that. In the 16th century, it was the English physicist William Gilbert who found that it was not an exclusive property of amber, that there was other substances which shared the same property. And he called this group of substances like electrics, and those electrics are substances or materials that contain electricity, and when rubbed they gain electric charge. So it was William Gilbert who gave these names for this set of properties. Later in 1733 it was the French chemist Charles-François de Cisternay who describes the two different electric charges. So he recognized that there are different charges, that they are two, and he called them vitreous and resinous electricity because the differences are attributed to given material. So it was not the same to rub like a bar of glass or vitreous material than to rub or to gain electric charge from a resinous electricity. So it was clearly differentiable that they were two different types of electric charges. It was Benjamin Franklin who assigned the vitreous electricity as positive charge and the resinous as the negative charge in 1740s. He did so without any specific method to design which is the positive and the negative charge. Just there were two possibilities, and he just assigned it by chance. Later, it was the Italian physicist Alessandro Volta who invented the electric battery and produced electric current, and doing so he demonstrated the relevance of electricity and the connection between chemical reactions and electric electrical current flow. And this battery is the instrument which was used by William Nicholson and Anthony Carlisle for the production of, or for the testing of, water splitting. Later on, it was another French chemist called Joseph-Louis Gay-Lussac who reversed Nicholson's water splitting reaction to produce water from hydrogen and oxygen gases. With this type of experiments, he published what is known like the law of combining volumes in 1808. This law is the equivalent to Prost's law of definite proportions but applied to gases, and he states that when gases combine to form compounds, they always do so in small whole number ratios. To understand this law, we should start with an example, or let us analyze an example of the formation of hydrogen chloride at constant pressure and temperature. We know that at a constant pressure, temperature, and a given volume, independent of the element, there will be always the same amount of particles, molecules, or atoms. So if you mix one volume of hydrogen with one volume of chlorine, what you expect is that they form one molecule of or some molecules of hydrogen chloride, and each molecule behaves like one particle. Therefore, if you mix 1 volume of hydrogen plus 1 volume of chlorine, you expect to get 1 volume of hydrogen chloride. However, it was not the case. When they did actual measurements, they found that the mixture of 1 volume of hydrogen combines with 1 volume of chlorine to form 2 volumes of hydrogen chloride, and this could be explained only if the original reactants, meaning hydrogen and chlorine, they were not composed, or these particles which are contained in this volume is not one single atom, but is a molecule, like for example the molecule of hydrogen, which in gas it has 2 atoms of hydrogen. The same happens with chlorine, and that's why when you mix 1 volume of this diatomic hydrogen with 1 volume of diatomic uh, chlorine, you will get 2 volumes of hydrogen chloride because the number of particles double. This was very important because based on this type of experiments, then it was possible to correct the table of atomic weights published by Dalton, and therefore they could find that the weight of oxygen, it was not 8 as previously proposed, but it was 16. And the same happened, for example, with ammonia for the weight of nitrogen and all the other mistakes and weights that was published by Dalton. This assumption on the volume which is occupied by different gases at a given temperature and pressure, it is known like the Avogadro's hypothesis, which was published in 1811 by the Italian chemist Amedeo Avogadro. And despite it could explain the example of the hydrogen chloride, his hypothesis was neglected for half a century due to the confusion between atoms and molecules. The knowledge about molecules it came much later. Mm, because of this, then the exact atomic weights of elements was still uncertain. And for example, based on Dalton atomic weights as integers of 1, because if you check again the table of Dalton, the atomic weights were always multiple of 1. Then another English chemist called William Prout suggested in 1815 that all the elements were a composition of hydrogen, and it sounds still like alchemist. So even at first, Proust's hypothesis it was published anonymously. So because he didn't want to take the risk to be called an alchemist, which was already seen like it was not well seen, the alchemy. So he first published it like anonymous, but it was found that it was suggested by him that all the elements were composed of hydrogen. It was later with the development of the law of atomic heat by Pierre-Louis Dulong and Alexis Thérèse Petit, which are two French chemists, that they discovered that the specific heat of elements varies inversely with the atomic weight. And it means that if two bodies, let's say X and Y, absorb the same amount of heat, but the atomic weight of X is double than Y, then the temperature of X will be only half of the temperature of Y. And this is important because it was one of the tools used by other chemists to validate the results of or the precision of the atomic weights published by Dalton. And we will see this. There was especially one person who worked on this. His name was Jöns Jacob Berzelius. He was a Swedish chemist, and his major contributions are on the determination of atomic weights with more sophistication than Dalton. His values were not generally whole numbers. Therefore, it was excluded the possibility that atoms were simply the mixture of hydrogen atoms or the conglomeration of hydrogen atoms. Another contribution was on the use of chemical symbols. Like we saw in the previous slides about Dalton, he used some symbols to represent atoms. Like for example, hydrogen was a circle with a dot, oxygen was only one circle, and when Dalton ran out of ideas, he started to put letters inside those symbols, like for example S for sulfur, but enclosed by a circle. And it was Berzelius that it was not need, or that the use of the circle was superfluous, and therefore uh, we should use only the initial of the Latin name of the elements to represent the single atoms. And this kind of notation is something we still use today. The use of these chemical symbols, it was not only for representation, but they also simplified the chemical formulas and the chemical reactions. And later on, it was used for applying the Lavoisier's law of conservation of mass and for the balance of chemical equations. Another contribution is that Berzelius is credited like the discoverer of cerium in 1803, selenium in 1818, silicon 1824, and thorium in 1829. About his life, we know that his father died when Berzelius was only 4 years old, and his mother married again, but also died when he was 8 years old. So he had a quite difficult childhood in that sense. We know he went to study medical at the medical university in Uppsala, and during this time he also studied German, French, and English, and he became quite proficient on those languages and published even in those languages as well. He graduated as a medical doctor in 1802, and he started studying chemistry when he was 19 years old, but it is said that he was better in physics than chemistry. Uh, Besides chemistry, or yeah, in his more applied life, he tried some business with the production of mineral water and other products, but it was not so successful. So he had also some problems with money at those times. And in 1807, he was assigned as a chemistry teacher in a school. And in 1808, he became a member of the Swedish Academy of Science. Uh, Being a member of the academy, he travels to England, and then he met with Humphrey Davy and Watt, which are important names in the field of electrochemistry, in chemistry, and development of what we know for the Industrial Revolution, these engines. And now we should talk again about Humphrey Davy. He was an English chemist, and at his time it was believed or presumed that some oxides contain elements that couldn't be isolated with the known techniques. And it was not so weird, because from ancient times they already knew that from metal oxides it was possible to isolate elements like the metals themselves. Like for example, from iron oxides, when heated with coke, it could be released the metallic iron. And before that, there are the examples of copper and yeah. However, for the case of other oxides like limestone or potash, coke was not enough to release or to separate the oxygen from the oxide and reveal the unknown element. And therefore, Humphrey Davy tried the method shown by Nicholson and Carl Lees. And Uh, Remember that this was electrochemical method, so electrolysis for water splitting. At first, Humphrey Davy he built a very large battery, those types of batteries developed by Volta, and he applied high currents to um, solutions containing these oxides, but he couldn't achieve the separation, only the water splitting. Later, he tried with molten products of these oxides, and he was able to isolate the secret elements. Using this method, he was able to isolate and discover for the first time potassium from potash. And 1 week later, he was able to isolate sodium. And later, he discovered other elements like magnesium, strontium, barium, calcium, and chlorine gas. About his personality, it's known that he was mm, very, very popular in London at his time. He gave very popular lectures on chemistry for common people and scientists. So he was very well known in society. Another contribution of him is that he demonstrated that oxygen is not a common component of acids, and in this sense, he corrected the original idea of Lavoisier, who suggested that oxygen was a substance that gives origin to acids, and that's why he gave this name for this gas. But maybe one of the major contributions from Humphrey Davy was that he discovered to Michael Faraday. So he contracted Michael Faraday like his assistant, and himself, I mean Faraday himself, he became to be one of the greatest scientists in history. About Faraday, we know that he was an English physicist, and he was mainly an experimentalist and without previous academic background. And this is explained because he was born in a poor family and very religious, and he started to work in a lithography, like repairing books or preparing books. And those books on which he worked during daytime, it is said that he was reading and studying from that same books. By coincidence of life, he got some tickets to see Humphrey Davy, one of his presentations in the Royal Society, and he was very impressed by him and by his resources, by his results, and he started to take notes about this kind of experiments he was doing and collecting all type of information related to that. Another coincidence is that Humphrey Davy once suffered an accident and he became blind for a while, temporary blind. And during that time, he was asking for help, for an assistant. And then he hired to the young Faraday. And at the time, Faraday showed to Davy his notes about this type of experiments developed by Davy, and Davy got highly impressed by this young guy and decided to contract him for a long term, not just for this temporary period. During this time, Faraday had to help Davy in everything, not only in laboratory work, but mainly about cleaning and assistance for him and his wife. But soon Humphrey Davy recognized the talent of Faraday and started to give him more and more responsibility. And to the point that after 8 years working together, Faraday already was in charge and supervising other experiments by other people for Davy. And after this time, he also was writing scientific papers for for Davy. Working with Davy, Faraday also got to know other important scientists like Gay-Lussac, that we discussed before, ampere, and volta, and all of them recognized this talent of the young Michael Faraday. In 1821, Faraday achieved one of his most important contribution, and is that he was able to convert electrical energy into circular movement. So he was able to take electricity and convert it to motion. And this is basically a motor. So this is called uh, Faraday's motor or engine. Because of this discovery or contribution, it is said that started some problems between Davy and Faraday, most probably because of envy, and therefore Davy put Faraday to work in other field outside of electricity, and gave him some task with optics that finally he couldn't achieve more or much on this field. But in that way, Davy kept Faraday, let's say, in the shadows. After Davy's death, Faraday returns to study electricity, and he had a simple but fundamental question, and is that if electricity can produce magnetism, then can magnetism produce electricity? And doing this type of reasoning and experiments on this field, he developed and discovered what is called like electromagnetic induction. That when you have a magnet um, moving through a circuit, then you can produce electricity. So in this case, he had both applications. In one sense, he could produce a motor or an engine from electricity, and on the other way, he could produce the electricity themselves by using a magnet. With these two contributions, and it is said that currently around 50% of the GDP of the world is based on Faraday's work. So it's a very, very impressive achievement of Michael Faraday to science. Later on, he started to work with the discovery or trying to understand how magnetism works. And in this time, it was thought that forces like this magnetism or like gravitational forces, they operate at distance. So this is called like the forces at a distance, meaning that they apply instantaneously between the bodies without the need of touching between each other. So, like for example, the gravitational force between the moon and the earth, that they are not touching themselves, but they experience the force emitted by their bodies in this case. And this force is instantaneously according to Newton's equations. However, what is shown by Faraday is that there exist electromagnetic fields, and it was simple to observe in a sense in the case of magnets when you see like iron ash or pulverized iron in the presence of a magnet, you can see the field lines, let's say. But besides this, he also did some experiments using glasses to prove the existence of electromagnetic fields. But all the previous was more related to physics. In the field of chemistry, Michael Faraday is related with electrochemistry. And for example, he was the first to term the electrolysis to the process of water splitting. And he also gave the name of electrolyte, electrodes, anode, cathode, ions, cations, and ions. So basically, he created all the terminology for electrochemistry. And he also gave two laws. So the first law of electrochemistry, which states that the mass of a substance liberated at an electrode during electrolysis is proportional to the quantity of electricity driven through the solution. And the second law of electrolysis, according to which the weight of metal liberated by a given amount of electricity is proportional to the equivalent weight of the metal. So with Faraday, we finish this session. And remember that next week you will have to take a test that will be available in the co-space, that you will have 2 hours, but you can take it anytime during the next week. So thank you so much for your attention.